All right, question 26. Compound X has stereoisomers and forms a precipitate when warmed with Fellings reagent. What could the structure of compound X be? Okay, a couple of really key bits of information here. One, that it forms a precipitate when warmed with Fellings reagent. Now, what this means is that compound X must be an aldehyde, okay? So it's an aldehyde. That's our first big clue, aldehyde. So just to remind us of the test with Fellings reagent, here's an image here. So Fellings is blue. The solution is blue, and there will be no change in color when it's warmed with a ketone, so it's going to stay blue. But when you warm it with an aldehyde, you're going to get an orange, orangey brown precipitate. Okay, so we know that compound X is an aldehyde. That means it's got to be either A or D. Okay, so it's either A or D because B and C, these are both ketones. So we're going to have to rule out B and C, so it's either A or D. And the second bit of key information here is it's saying that it has stereoisomers, okay? Now, stereoisomers can be divided into two categories, okay? We've got cis trans. Sorry, it takes me ages to write with a mouse. We've got cis trans isomers, or we've got optical, okay? I actually call the optical ones chiral because it helps me remember exactly what I need to look out for. So cis trans is because you haven't got free rotation about the double bond. So when you're looking for cis trans isomers, you're looking for a carbon to carbon double bond, okay? And you're looking to see if they've got different things attached to the carbons, right? So if we look at A here, if I draw in my carbons here, right, then this would be a methyl group, and this would be a methyl group. Okay, so we can't have cis-trans isomerism here because we've got two of the same groups attached to that carbon. So if you switch them around, okay, you've got the same thing. So we don't have cis-trans isomerism here. So we don't have cis-trans in A. Do we have optical isomerism? Well, I call this chiral isomerism because what I'm looking for is a carbon, a central carbon that is bonded to four different things. And that means it will deflect light a little bit differently. We don't need to worry about the complications of why, but what we're looking for something that has optical isomers, we're looking for a central carbon that is bonded to four different things, different groups or different particular elements. So that's known as a chiral center. So in this case, right, there's no chiral center. Okay, so here basically, if we look at this one, which is the only one that's bonded to four other things, but they're going to have two hydrogens here, aren't they? So this carbon, despite having the four separate bonds here, two of them are the same. So that wouldn't classify as an optical isomer. So the answer is going to be D, and we've just done that by ruling out the other three. But let's look at exactly why the answer is D. Well, it doesn't have cis-trans isomerism because there's no carbon-to-carbon double bond there, but it does have optical isomerism. If I just hone in on this area here, I draw in the carbon here, okay? I've got a methyl group here, that would be a CH3. And then I've got, this is the rest of the carbons in the chain, isn't it? I'm not going to carry on drawing, but I'll draw that first one there, and it's two hydrogens. And here I've got a hydrogen, and then here we've got our aldehyde group. Now, you can see that this carbon here is a chiral center because it is bonded to four totally different things. We've got a methyl group, we've got our aldehyde, part of the compound, we've got a hydrogen, and then we've got a 1, 2, 3 carbon chain here. So that would be propyl. We've got a propyl group. So I'm just going to draw circles around those four different things. 1, 2, 3, 4. So we have a chiral center. So this will have optical isomerism. So that's why the answer is D. I hope that has helped.